Okay, so what if I told you that a pretty simple design question, how to build the perfect rectangle, actually holds the key to a really powerful problem-solving technique? Today, we're going to dive into a challenge that's all about finding that perfect balance between length and width. And trust me, the solution is surprisingly elegant.
So, let's warm up with a super simple example. Imagine your target area is 4. How would you design the best rectangle? It seems pretty easy, right? I mean, you could have a 1x4 or a 4x1 or maybe a 2x2 square. But what makes one of those the best? That's the real puzzle here, and the answer isn't as obvious as you might think.
And this gets us to the heart of what's called the construct the rectangle problem. A good way to think about it is like you're a web developer, and you're trying to figure out the perfect dimensions for a page layout. You're given a specific target area, and your job is to find the ideal length L and width W.
But here's the catch. We can't just pick any two numbers that multiply to our target area. Nope. To find the best rectangle, we've got to follow 3 very specific rules. These rules are what will narrow down our options and lead us straight to the optimal design.
Let's break these down. First, length times width has to equal the target area. Okay, that makes total sense. Second, the length has to be greater than or equal to the width. And third, and this is the big one, the difference between the length and width needs to be as small as possible. That last rule is really what turns this from a simple math problem into a genuinely interesting design puzzle. So that second rule is clarified perfectly right here. For an area of 4, a rectangle with a length of 4 and a width of 1 is totally valid. But a tall and skinny one with a length of 1 and a width of 4, not allowed. So we're always looking for shapes that are wider than they are tall, or, perfectly square. And this table just brilliantly illustrates that third crucial rule. Look, both 4, 1, and 2, 2 are valid options for an area of 4 if you only look at the first 2 rules. But when we check the difference between length and width, it all becomes crystal clear. A difference of 3 is way bigger than a difference of 0 for the 2, 2 square. So boom, the 2, 2 square is our optimal solution. We're basically hunting for the most square-like shape we can possibly make. Okay, so we know what we're looking for, but how in the world do we find it efficiently, especially if we're dealing with a huge area? We can't just check every single pair of numbers. Well, it turns out there's a clever trick, a real aha moment that just cuts right through all that complexity.
Seriously, let's just think about this for a second. If you had a massive area, like 122,122, trying to test all the possible pairs of factors would take forever. There has to be a smarter way, a more direct way, to find that most square-like pair. What do you think?
The answer lies in the square root. Yeah, that's simple. By starting our search right in the mathematical middle of the problem, we can find our solution incredibly fast.
This is the key idea right here. The factors of any number that are closest to each other are always hanging out right around its square root. So for a perfect square like 36, the square root is 6, and the factors are 6, 6. Makes sense. For a number like 35, the square root is about 5.9. And guess what? The closest factors are 5, 7. See the pattern?
So here's the game plan. We start our search for the width, W, at the whole number part of the area's square root. Then we check, does it divide the area perfectly, with no remainder? If it does, we're done, we found our answer. If not, we just count down by 1 and check again. The very first number that works is guaranteed to be the best possible width.
All right, so that logic is pretty slick, right? Now let's see how this elegant idea translates into a surprisingly simple and really powerful piece of code.
We're going to look at a Python solution. And get this, it's only 3 lines long. But each of those lines is doing something very specific and, frankly, very smart.
So line 1 puts our core idea right into action. We just calculate the square root of the area and then chop off the decimal part to get an integer. This gives us the largest possible value that the width W could ever be, making it the perfect starting point for our search.
Now for the search itself, this while loop is unbelievably efficient. That %sign, that's the modulo operator. It just checks for a remainder after division. So this loop is basically saying, hey, as long as the area isn't perfectly divisible by our current width, just subtract 1 from the width and try again. It's just a simple countdown to find the first perfect divisor.
And once that loop stops, it means we found our perfect width, W. The final step is to figure out the length. That double slash just means integer division. So we divide the area by our width to get the length, and then we return our final answer, the pair L, W. And that's it. So there you have it. That's the solution. But honestly, the most important part is really understanding why this strategy is guaranteed to give us the right answer every single time. It's not magic. It's just really solid logic.
Here's the bottom line on why this works so perfectly. Remember rule number 2, length has to be greater than or equal to width. Because of that, the width can never be larger than the square root of the area. So, by starting our search at the square root and counting down, the very first factor we find is guaranteed to be the largest possible width. And a larger width automatically means a smaller length, which in turn gives us the smallest possible difference between them. It's just an elegant and perfectly logical solution.
So, the next time you're faced with a problem that's all about finding an optimal pair or trying to balance two competing factors, remember this square root secret. It's a powerful reminder that sometimes the most efficient path to a solution isn't starting at the beginning, but right in the middle. So the question is, where else can this way of thinking